we saw in the last session how the physical properties of solids depend rather strongly on the symmetry properties. However, there is one class of solids in which the details of the lattice structure does not play a very big role on the physical properties. These are metals such as gold, silver, copper and so on. These metals, their behavior can be understood on the assumption that each atom donates, in the case of a monovalent metal, one electron to the metal, and this electron is usually the outermost one in the metal atom. For example, in the case of sodium, which has an atomic number is the number of electrons of 11, Z is the usual symbol. There are 11 electrons in the sodium atom, of which 10 of them go into the so called 1s, 2 electrons go into the 1s shell, and then 2 electrons go into the 2s shell, and then 6 electrons go into the 2p shell. So, this is the so called closed shell structure. Out of these 11 electrons, 10 of them go into the closed shells, leaving only 1 electron in the outermost 3s shell. So, this electron, which is the outermost in the metal atom, this is just an example. Similarly, one can look at any metal atom and then analyze this. The outermost electron is available for conduction, because it is rather weakly bound to the parent atom and therefore can be ionized rather readily, and this outermost electron is known as the conduction electron, because this gets ionized and this electron becomes available and is free to wander around inside the metal. So, it is very much like the atoms and molecules in an ideal gas. So, one speaks of an electron gas in this case. So, this means that even though the metal is a condensed system, a condensed matter, a solid, but the electrons inside it are behaving very much like the atoms and molecules in an ideal gas. One might ask, what happens to the Coulomb repulsion between the two electrons, pairs of electrons? This inter-electron repulsion is rather weak in comparison to the attraction between the electrons and the positive ions, which are left behind after the ionization. So, one neglects it to a first approximation inter-electron or Coulomb repulsion is overlooked, ignored to start with, so that one can think of free electrons which are not strongly interacting. Free electrons are free in the sense that they are free for conduction to carry electricity. inside. That is why metals are such good conductors of electricity. Only thing is, these electrons, the ideal gas molecules or atoms are classical particles, whereas electrons are quantum particles which obey electrons are known as fermions. Fermions means they obey so called Fermi Dirac statistics rather than not Maxwell-Boltzmann statistics. So, their collective behavior is not described by classical Maxwell-Boltzmann statistics, which is obeyed by ideal gas molecules and atoms, but when we discuss the properties of this electron gas, we have to take account of the fact that they obey Fermi Dirac statistics. So, we have to use Fermi Dirac statistics in order to describe their collective behavior. This is a rather important factor, the Fermi Dirac distribution function. I will write it as FD for short. The Fermi Dirac distribution function has the following form. F of E, that is the distribution function which describes how the electrons are distributed into the various energy states. So, the system of electrons has different energy levels, the electron energies are different, and therefore, the electrons occupy these energies, and the way they are distributed in energy is given by this function 1 by exponential E minus E f by k b t plus 1, where k b is the Boltzmann constant and E f is known as the Fermi energy. Kb is a universal constant, as you know, and the Fermi energy is a characteristic of the metal. Now, everything will depend, the collective behavior will depend on the statistical distribution, how the electrons are distributed in energy. Therefore, let us look at how this function looks. This function is plotted in this figure. Let us look at the figure on the left side, which gives the value, this function plotted at absolute 0. Let us discuss the behavior of the metal at absolute 0, and then we can go to finite temperatures. This is simpler. So, you can see that this function looks like this. So, if I have the Fermi energy here, then this is 0, this is 1, so that is the behavior of this function at absolute 0. So, this is at 0 k. What does this say? The physical meaning of this picture is that if you look at all states, all energies which are less than the Fermi energy, if you look to the left of this EF in the graph on the energy axis, all these states are occupied with a probability of unity, in the sense that this means that they are fully occupied. These states are all completely occupied by the electrons. None of these states is empty. All the states below EF are all occupied by electrons. This, whereas all the states above EF, the Fermi energy, are completely empty. They have 0 probability. The F of E is 0. So, the probability of occupation of these states above the Fermi energy at absolute 0 is 0. That means that they are completely unoccupied. This is because the electrons obey what is known as Pauli exclusion principle. That is why they are fermions. This means that if one state or one energy level is occupied by an electron, then another electron cannot be found in the same state. It is excluded from occupying the same state. So, each state is occupied by an electron, and you have all these states below EF occupied. Well, this picture is slightly modified at finite temperatures, but we will come to that a little later. This is enough for us now. So, if this is so, at 0 Kelvin, the Fermi level EF is the highest occupied state. Now, of course, when I say that each state is occupied by one electron according to the Pauli principle, what I mean is that we do not consider the spin of the electron. If you consider the spin of the electron, then we know that electron has a spin of half, and so can occupy two states with parallel or anti-parallel spin to a given direction in space. Therefore, these two electrons with opposite spins both have the same energy, and so each of these states can be occupied by two electrons with opposite spins without violating Pauli principle. We will remember this. But the spatial energy of these electrons is simply given by the kinetic energy, which is h cross square k square by 2m, where h cross is h by 2 pi, h is the Planck's constant, k is the wave number, which is equal to 2 pi by lambda. We already talked about lambda as the de Broglie wavelength, and m is the mass of the electron. So, the energies of the electron in these states is given by the wave vector k, and this is just the kinetic energy h cross square k square by 2m. Now, why do we need this? We need this information in order to calculate, for example, the number of electrons, conduction electrons inside a metal. The metal is now somewhat like a box within which this electron gas is free to wander around, but the electron is not allowed to escape out of this metal. So, that is the only constraint on the electrons. So, within the metal they are free to wander around, very much like the atoms and molecules of a gas. So, next we wish to calculate the concentration of electrons, which is the number of electrons per unit volume. When I say electrons, I only mean the conduction electrons. In order to find this, we have to also consider, in addition to the distribution function, we have to consider what is known as the density of states. This is because the distribution function tells us how the electrons are distributed in energy, but as you can see from this equation connecting the energy and the wave vector or the wave number, it is the wave number which decides the electron state. So, we want to also know how the conduction electrons are distributed in different states corresponding to a given energy. So, this is given by what is known as the density of states. So, it tells us how many states are available in a differential energy interval adjacent to a given energy. So, if I look at a particular energy, so I look at an infinitesimal dE around a given energy. So, if I take this infinitesimal energy interval, we d of E is the density of states function, which describes d of E dE gives the number of states in this energy interval. So, we wish to find out this density of states. Together the distribution function f of E and the density of state function d of E dE together will determine the average, the statistical properties of this electron gas. How do we find this density of states function? We will just discuss this next. So, we know that the energy is just p square by 2 m, because the electrons have only kinetic energy. So, dE is p dP by m. Now, if I look at the momentum space and if I regard the Fermi energy as corresponding to a value which corresponds to an isotropic Fermi surface, which means it is a spherical Fermi surface. So, it is a sphere with radius F in energy space. So, that is the Fermi sphere. And all the states inside this are occupied by the electron gas. So, we know that the radius, the volume of this, the differential volume is 4 pi p square dP. This is the differential volume in momentum space. Position and momentum together define a state in statistical physics. So, this is the differential volume in momentum space. If we take the now we count the number of states in this interval by writing d of E dE equals V, the actual volume in real physical space, the position space, multiplied by the differential volume in momentum space times 2, the factor 2 in order to take into account the spins, and divide this by the volume of a phase cell in phase space. Cell means state. Each cell, each of these cells corresponds to one state of the electron, as we discussed already according to the Pauli principle. Now, this volume of a cell in phase space is given by the so called uncertainty principle in quantum mechanics. As I already told you, the electrons are quantum particles. So, we have to discuss their statistical behavior according to the quantum statistics, and Fermi Dirac statistics is a quantum statistics. Now, the main feature of quantum behavior comes from the so called uncertainty principle due to Heisenberg. This principle states that the product in uncertainties of position and momentum is of the order of the Planck's constant, and therefore, this is in one dimension. Therefore, we can write the volume of a cell in phase space as the product of the uncertainty. You cannot locate a particle beyond this accuracy in quantum mechanics. So, this is the minimum uncertainty. So, this is the spatial and momentum extent, the extension in space and real space and momentum is given, is of the order of the Planck's constant. So, if we use the same argument for all the 3 dimensions in real space and all the 3 components of linear momentum, then we get this volume is h cube. This is h for each dimension. So, there are 3 dimensions. So, each time it is multiplied. So, you get h cube, and that is the uncertainty to which you can locate a given state in phase space in quantum mechanics. Therefore, that corresponds. So, the space, the phase space in quantum mechanics is coarse grained, and this is the volume occupied by a state in phase space. So, you divide this total volume available, the physical volume V times the differential volume in momentum space times the factor 2 due to spin states, and divide the whole thing by h cube. That will give you the number of states, which is in turn given by dFE dE. So, this gives us the way to calculate the density of states function. Therefore, we just substitute p square is just 2me. So, 4 pi, so p is 2me to the power half. So, here I have p square dp, which I can write as p times p dp. P dp already I have as mde. So, 2me to the power half times mde. Therefore, substituting here dFE dE is 2v into 4 pi into p square dp, which is here 2me to the power half into mde by h cube. So, this on simplification gives you the density of states function as 4 pi v. So, you can see that this is the density of states function, which is plotted in this figure. So, you can see the density of states goes as e power half. Now, we have developed all the things that we need to evaluate the electron concentration at 0 Kelvin. Let us do this now. So, the number of electrons in unit volume is the total number divided by the volume, and that will be, this total number is what is given by this. So, I have 1 by V integral d of E f of E dE from 0 to EF. This is because f of E gives you how the electrons are distributed in energy, and d of E gives you how the energies are distributed in states, and therefore, the product of these two integrated over an energy interval from 0 to the Fermi energy, up to which all states are completely occupied, rest of them are completely empty. So, it is enough if I can integrate it over all the energies from 0 to EF. Let me write EF at 0 in order to remind ourselves of the fact that we are calculating it at 0 Kelvin. So, if I substitute these 1 by V 0 to EF, then I have all this 4 pi V into 2m to the power 3 by 2 by h cube e power half d, and I have removed f of E because this is going to be 1 for all these states. So, it is going to have a value 1 at absolute 0. So, we can write this, all these constants can be factored out, V cancels off 4 pi 2m to the power 3 by 2 by h cube E of 0 to the power 3 by 2 into 2 by 3 as a result of integration. So, that gives me the final result as using this and using EF, as we already saw, EF is nothing but the kinetic energy up to the wave vector at Fermi energy, h cross square kf square by 2m. Therefore, we get N as so that gives you a rather compact relationship between the Fermi wave vector at absolute 0 and the electron concentration n. Now, we assume that because, for example, in a metal like sodium, each atom donates 1 electron to the conduction band. So, if we have a mole, a gram atom of this solid, then this will contain, as is well known, an Avogadro number of atoms. So, that corresponds to the number of electrons donated, conduction electrons donated. So, if you take the Avogadro number and divide by the atomic weight, so that gives me, see, 1 gram atom or kilogram atom corresponds to Na number of atoms, and that each atom gives you 1 electron in a monatomic solid. So, this is the number of electrons. So, this corresponds to a weight of A, where this is the atomic weight. Therefore, the number of electrons is just in 1 mole is Na by A. Times we are forgetting the fact that we have also rho, because this gives you the number of electrons per unit mass, and then we have to multiply this by the density. So, we can calculate n and therefore, calculate the Fermi wave vector and in turn the Fermi energy. So, we have a way of calculating the Fermi energy, from this formula. So, the Fermi energy values calculated in this way are all shown in the table. So, the Fermi energy at 0 Kelvin, the values are given in electron volts, which is a convenient unit in the case of atomic physics. This gives you the energy of an electron when it is accelerated through a potential of 1 volt. Now, the various metals, aluminum, copper, gold, potassium, silver, sodium, you can see that the Fermi energy varies from something like 11.6 electron volts to 3.2 electron volts. In any case, they are all of the order of electron volts. So, this is a very important idea, because if you convert it by using Boltzmann constant into equivalent temperature, this would be of the order of 10 to the power 4 Kelvin. So, a very high temperature. So, the energy is, the Fermi energy corresponds to a very high temperature, the corresponding temperature in temperature units. So, now we will use these concepts to calculate an important thermal property, namely the electronic specific heat. This means that this electron gas, if you inject some heat energy into it, the electrons absorb this energy and their temperature goes up. So, the specific heat is defined as the rate of change of the mean internal energy of the conduction electrons at 0 K with respect to temperature. So, the electronic specific heat can be calculated by calculating the average energy of this electron gas, which is simply done by, again at absolute 0, this is done by integrating from 0 to E of 0 of E d of E f of E d by 0 to E of 0 of d of E f of E d. So, this gives, going by the same procedure, we arrive at the result, this is 3/5 of E of 0. The average energy is 3/5 of the Fermi energy at absolute 0. Now, the electronic specific heat, having got the average energy, we can simply differentiate this expression for the mean energy with respect to temperature. That gives you the electronic specific heat. Now, we will first qualitatively see what kind of results that we are going to get for this calculation of the electronic specific heat. Since we said that the E of 0 is of the order of 10 to the power 4 Kelvin in temperature units. So, if you thermally excite, usually thermal excitation is at best of the order of 100 Kelvin. So, it is a very small, if you go back to the energy distribution, this is EF at 0. If you go back to this, this is of the order of this in temperature units is of the order of 10,000 Kelvin, but our energy excitation, thermal energy excitation is only of the order of 100 Kelvin. So, it is a small temperature window. So, the excitation is going to shift states from this to this, but these states are all, remember that they are all completely occupied and are subject to, the electrons are subject to Pauli exclusion principle. That means, if a state is completely occupied already, you cannot put another electron in this. So, this excitation from this one occupied state to another occupied state in this whole range is not going to be possible. Even though you give the excitation, the electrons cannot be excited from an occupied state here into another occupied state, which is not empty. So, this is only possible only at this edge, this is not possible, and the thermal excitation is only possible here. So, this is of the order of 10 to the power 4 Kelvin, and this is of the order of 10 square. So, this is only possible from across this Fermi energy. If you bring it close here, so it can excite across into one of the empty states here. So, only the fraction of electrons which occupy states within this 100 Kelvin in the neighborhood of the Fermi energy, only they will be able to get excited. So, what is this fraction? They are kBT by kBTF. kBTF corresponds to all the states, the electrons in all the energy scale, and kBT corresponds to the energy of the thermal excitation. So, this is the fraction which is T by Tf, that is the fraction of electrons excited. Excited thermally. And each of them has an excitation of the order of kBT. Therefore, the excitation energy is of the order of kBT square by Tf. So, d by dt of this gives you the specific heat. So, this is of the order of kBT by Tf. So, this tells me that the electronic specific heat is of the order of kBT. It is proportional to the temperature T. So, the electronic heat capacity or CE, the electronic specific heat is equal to a constant times the temperature. So, that is the basic result that we get for the electronic specific heat of the conduction electron gas. So, you get this is the value at absolute 0. So, this is shown graphically. So, in figure, of course, you will never be able to measure the electronic heat capacity alone. It will be also the total specific heat, which includes the contribution from the electrons and also from the lattice of ions or the atoms in the solid, and that, as we will see later, is given by the Debye theory of specific heats, and that temperature dependence is a T cube dependence. So, the overall behavior is given by a relation of this kind, C total. And therefore, if you plot C by T versus T square, that would be a straight line. That is what is shown in figure. So, from the intercept of this, we can get the heat capacity coefficient gamma. Well, we have discussed everything at absolute 0, but the question arises, what happens when you have electrons at a finite temperature? This is a bit more difficult to calculate. We will not go through the details of this calculation here, but I will just roughly indicate what happens by looking at the distribution function. So, at a finite temperature, the Fermi Dirac distribution function, this is at a finite temperature which is not 0. So, the distribution function now deviates from the behavior at absolute 0. This is at 0 Kelvin, as we have already seen. And at a finite temperature, this reduces to something like this. That is the behavior at T not equal to 0 K. At any finite temperature, the FFE decreases from the value 1 to something like half at Fermi energy, and then it goes on beyond, it is non-zero even beyond EF. This means that some of these states are empty even before, even below the Fermi energy, and some of these states are above the Fermi energy or occupied. And this, the number of occupied states goes on increasing. So, this is the behavior, and this will modify the Fermi energy. The Fermi energy will be a function of temperature now, and the heat capacity coefficient, which is still found to be a linear function of temperature, but the constant, the linear heat capacity coefficient is slightly different. We will not calculate this, this is the overall behavior. Now, this electron gas also possesses many other interesting properties. The electrons have a magnetic moment because of their spin, and this contributes to paramagnetism. So, this is known as Pauli paramagnetism. Or this is a spin susceptibility. This is a magnetic susceptibility which arises from the fact that the electrons have spins and therefore a magnetic moment. So, this is another important characteristic of the conduction electron gas in metals. In addition, the metals, most important characteristic is that a metal is a very good conductor of electricity. Now, we would like to have an expression for the electrical conductivity of a metal and how it depends on, for example, the temperature, and not only the electrical conductivity, a metal is also a good conductor of heat. So, we would like to know how the thermal conductivity is determined by the behavior of the electron gas. We also know that there is such a thing called the thermoelectric power, the phenomenon of thermoelectricity, in which metal junctions are used in order to produce a thermoelectricity, an EMF. So, we would also like to know how the thermoelectric power of a good conductor is determined by the behavior of the electron gas. These are things that we will discuss in the next lecture.